All right, diving in today, and we've got a really fascinating paper. It's called Cost Optimal Grouped Query Attention for Long-Context LLMs.
Okay.
And what really caught our eye with this one, it's all about efficiency. Like, how can we make these big, powerful LLMs, the large language models, how can we make them work better when they've got tons and tons of text to deal with?
Right. Yeah. It's a big deal. I mean, just the resources to train these things, especially with everyone wanting them to understand longer and longer context, it gets expensive fast.
Oh, yeah. No, absolutely. And the paper's really tackling that head on.
Yeah.
They're looking at a core part of how these models work, this thing called the attention mechanism. And they're saying, hey, we can make this way more cost effective. And that's huge, right? Because think about what we're asking these models to do now, summarizing a whole legal document, having a back and forth conversation that lasts for hours, analyzing thousands of lines of code.
It's why.
The memory, the computational power just goes through the roof.
Yeah.
And so this paper, it's like they're trying to find this perfect balance point between how well the model performs, its size, how much text it can handle, and then this whole thing about how it focuses its attention. This thing called Grouped Query Attention, or GQA.
Yeah, GQA.
So right off the bat, what I found really interesting is they're saying, when you've got a really long sequence of text, sometimes having a bigger model, but with fewer of these attention heads, can actually give you better results. And not only better results, less computation, less memory.
Yeah, and that's really counterintuitive, right? Like you'd think, oh, bigger model, more power, gotta be better.
Right. More is always better. Just keep scaling up.
Exactly. But they're showing that, especially with this long context stuff, there's a smarter way to do it. It's not just about brute force. It's about optimizing how that attention mechanism works.
Okay, so let's get into the nitty gritty here. They start off by laying out the problem, right? What were they seeing is the limitations with how people were approaching these long context LLMs?
Well, their main point is that, everyone's been focused on making these models bigger. More parameters, more training data, more computing power. But they haven't really looked closely enough at how the length of the text and the way you configure those attention mechanisms, especially this GQA, how that affects things.
Yeah.
And they argue that a lot of the current implementations of GQA, they have these kind of artificial restrictions, like they tie the number of attention heads directly to the model's hidden dimension.
Okay.
And they also say that the existing scaling laws, the ones that try to predict how well a model will perform based on its size and data, they don't fully account for how context length really drives up those costs.
So what's their solution? How do they propose we change things up?
They took a really systematic approach. They basically ran a bunch of experiments, comparing models with different sizes, different context lengths, and most importantly, different configurations of those attention heads. And what they did that was kind of clever, they decoupled the number of attention heads from the model's hidden dimension.
Okay, so break that down for me. Decoupled. What does that mean in practical terms?
So think of the hidden dimension as like the brain power of the model, its capacity to process information.
Okay.
By separating the number of attention heads from that, making it its own thing you can adjust, they had a lot more control over how the model was using its resources.
So it's like fine-tuning, getting really granular with where the computational effort is going.
Exactly. And then they went even further. They took those existing scaling laws for LLMs and actually expanded them to include context length and the attention head configuration. This let them create a much more realistic model of how well the language understanding would be, taking into account not just the usual stuff, but also the actual computational and memory costs, especially for these long sequences of text.
Okay.
And one of the really significant things they found was this relationship between how well the model performs, like its accuracy, or conversely, its loss, and the number of attention heads it has.
Interesting. So fewer heads might actually be better in some cases.
That's what they're suggesting, yeah.
All right. So what were some of the big takeaways from their experiments? What kind of data were they working with to back up their claims?
Well, first off, they found that decoupling the number of attention heads from the hidden dimension, it really does let you use your computing resources more strategically. You can really tailor the architecture to the specific task.
Makes sense.
And second, they showed that those traditional scaling laws we've been relying on, they're kind of limited because they don't fully account for the costs of that attention mechanism when you're working with really long text, especially during inference when you're actually using the model to do something. And then there's the memory demands of the KV cache.
Okay, refresh my memory here. The KV cache, that's what lets the model keep track of what it's already seen in a sequence, right?
Exactly. That's the memory. And they actually give you formulas, like equations for calculating the computational cost during inference infer and the memory cost minferty. And these formulas, they directly include the context length, the number of query heads, NH, the number of key value heads, NKV, and all the other parameters that go into defining the model's architecture and its computational demands. So you can really see where the resources are going. They also looked at the costs during training, and they found that the costs that aren't tied to the model's parameters, like those from attention, they might not have as big an impact on the overall training costs, especially when you're training mostly on shorter sequences.
Interesting. So the context length really is a key factor.
Absolutely. And for the experiments themselves, they based their architecture on Llama 3. Which is a pretty big deal in the LLM world right now. And they basically played around with the model size, meaning the number of layers and the hidden dimension, as well as those attention head numbers, NH and NKV. But they kept some things consistent, like the ratio between the hidden dimension and the number of layers and the size of each individual attention head.
Okay. So controlled experiment.
Exactly. And for training data, they use this massive data set called SlimPajama. It's got something like 627 billion tokens. That's a lot of text.
That's mind-boggling.
It is. And one of their key findings when they were looking at a super long context length, like 128,000 tokens, they found that a larger model with fewer query and KV heads, they give the example of H&8.1, could perform just as well, meaning have the same loss or accuracy as the standard Llama 3.21b model.
Wow.
But it used about half the computation and memory during inference.
That's huge. A 50% reduction. That's not just a little tweak.
Significant.
Yeah.
And another interesting thing they observed is that the relationship between the model's loss, like how wrong its predictions are, and the number of attention heads, NH, it follows this specific mathematical pattern, a power plus constant function.
Okay.
And this pattern seems to hold true no matter how big the model is or how long the context is, although I do say it might break down if you have a crazy number of heads. But the point is, adding more and more attention heads, you eventually hit a point of diminishing returns.
So you're not getting enough bang for your buck in terms of performance for all that extra computation.
Right. And when they kept the number of KV heads constant, and just changed the number of query heads, they saw this logarithmic relationship between the loss and NH. They also highlighted that the benefits of using fewer heads become even more pronounced the longer your context is. And then lastly, they showed that you can actually take a model that's been trained on shorter sequences and then fine-tune it on longer ones, and it can perform just as well as a model that was trained from scratch on those long sequences.
So that's really practical, right? You don't have to start from zero every time.
Exactly.
So if we were to try and sum this all up, what's the big takeaway for our listeners? Why does this research matter?
Well, I think the biggest thing is that it gives us some really practical guidance for building more cost-effective LLMs, especially for those applications that need to handle really long chunks of text. It challenges this assumption that the number of attention heads should always be linked to the model's hidden dimension. And it shows that fixed GQA configurations aren't always the best. It opens up a lot of new possibilities for designing these models.
Of course, no research is perfect.
Yeah.
What were some of the limitations that the authors themselves acknowledged?
Well, they were upfront about the fact that they mainly focused on FLOPs, which is floating point operations per second, basically a measure of computational cost, and memory usage as their main proxies for efficiency. But they acknowledged that in the real world, the actual speed of a model, how quickly it can process things, can also depend on the specific hardware you're using.
Yeah, different chips and all that.
Right. And they also mainly looked at transformers that use GQA. They didn't really explore other attention mechanisms that might be even more efficient. Although they do think that the general idea of balancing different types of costs could still apply to those other approaches.
Okay. Now, to put this into a bit of historical context, can you walk us through how we even got to GQA in the first place?
Sure. So way back in 2017, the original transformer architecture, that's where multi-head attention, MHA, came from. And in MHA, every attention head does its own thing, completely independent, which can be computationally expensive, especially during inference, when the model's actually generating text step by step. And to deal with that, along came multi-query attention, MQA. And the big thing with MQA is that all the attention heads share the same key and value projections.
Okay.
Which makes the KV cache much smaller during inference, so things run faster.
So MQA was a big step towards making inference more efficient.
Exactly. And then we get to GQA, which kind of sits between MHA and MQA. In GQA, the attention heads are divided into groups, and the heads within each group, they share those key and value projections.
Okay.
So you can think of MHA as like each head is its own group, and MQA is all heads in one big group.
Okay.
And a lot of the state-of-the-art LLMs today, they actually use some form of GQA. And this paper, it's building on that, trying to figure out how to best optimize that grouping strategy.
So earlier you mentioned scaling laws. How does this paper fit into all the work that's been done on that front?
Yeah, so scaling laws, they really started getting a lot of attention around 2020. There were these papers, Kaplan et al., Hoffman et al., that showed these relationships between how big a model is, how much data you use to train it, and how well it ends up performing. But as this paper points out, those earlier scaling laws were mainly focused on the number of parameters and the amount of computation during training. They didn't really consider context length or the specifics of the attention mechanism, especially during inference when you have to deal with that memory overhead. And what this new research does, it basically extends those earlier scaling laws, giving us a more complete picture of the real costs of using these models, especially when you're dealing with long contexts.
So it's like they're filling in a missing piece of the puzzle.
Exactly. And before this, were there other things people were trying to make these long context models more efficient?
Yeah, I mean, people have been working on this problem for a while. There are things like sparse attention, where the model only pays attention to certain parts of the text.
Right.
And then there are ways to compress the prompts to make the input shorter. And people have been trying to compress the KV cache to save on memory. But what's interesting about this paper is that they're focused on optimizing the GQA architecture itself. They're saying, look, even within this mechanism that everyone's already using, there's still a lot of room for improvement. And it's even possible that the things they've found could be combined with these other techniques to get even better results. It's like layering the optimizations.
Exactly.
Okay, so just to recap some of the key points we've covered that aren't just repeats of what we've already said. First, this idea of directly linking the hidden dimension to the number of attention heads is not always the best way to go, especially with long sequences.
Right.
Second, by really fine-tuning the number of query and KV heads, you can actually save a lot on computation and memory without sacrificing performance, and you might even get better performance. Third, the best configuration for those attention heads, it really depends on how long you expect those text sequences to be. And for longer contexts, it's usually better to have fewer heads and a bigger model overall if you're trying to stay within a certain budget. And finally, there's this predictable relationship between the number of attention heads and how well the model performs.
Absolutely. And all of this has some really practical implications.
Oh, for sure.
Think about things like legal documents, scientific papers, giant code bases. If you're working with that kind of stuff, the optimizations they're talking about in this paper could really bring down the cost of running these LLMs.
Yeah. Makes these technologies a lot more usable for everyone.
Absolutely. And for the companies that are building and running these models, like the cloud providers and the big tech companies, they can use these insights to make their models more efficient, which means lower costs for everyone who uses them. And being able to get the same or even better performance with less memory, that's a big deal for running these massive models on hardware that's not top of the line. It's definitely something that the big players in the field, OpenAI, Google, Meta, they're all going to be paying attention to this as they push those context window sizes further and further. And the fact that they used Llama 3 in their research, it really shows how relevant this is to what's happening right now.
Okay, now for our novel notions segment. Based on all this research, what are some of the more out there research directions that come to mind?
Well, one thing that really struck me is how the best attention head configuration seems to be tied to how long the context is. And that made me think, what if a model could actually change its attention head configuration on the fly, depending on how long the input is?
So it's like it's adapting to the situation.
Exactly. It would analyze the input, see how long it is, and then adjust the number of query and KV heads it's using. You could imagine some kind of gating mechanism, or maybe even a hierarchical attention structure where different levels are optimized for different context lengths.
So it wouldn't be stuck with one configuration. It'd be like, okay, short question, I'll use more query heads. Huge document, got to conserve resources, fewer heads.
Right. And the research definitely shows that different context lengths really do benefit from different numbers of those query and KV heads. So a model that could do that, it could handle all sorts of input lengths without sacrificing efficiency. Of course, the tricky part would be figuring out how to make that adjustment happen in a way that's not super computationally expensive itself.
Yeah, that's a whole other challenge.
But if you could do it, you'd have these incredibly versatile models.
Really interesting idea. Any other novel research avenues come to mind?
Well, another thought I had is that this paper, they were really focused on these decoder-only language models. But what about all the other transformer-based architectures out there? Like the encoder-decoder models that are used for translation or summarization.
Right.
Could you apply the same principles there, like decouple the attention heads and optimize their configuration? And would the best strategy be different for the encoder, the part that processes the input, versus the decoder, which generates the output?
I guess that makes sense. The encoder and decoder, they're doing different things, so maybe they have different efficiency needs.
Exactly. The encoder, it needs to understand the whole input sequence, so maybe it would need a different attention head setup than the decoder, which is just focused on creating a coherent output. And the main argument of this paper that you can get big efficiency gains by being flexible with how you allocate resources within the attention mechanism, that seems like it could apply more broadly. So looking at how decoupling the attention heads affects things in these encoder-decoder models for different NLP tasks, it could lead to some pretty big improvements. And it might even give us a better understanding of what those query and KV heads are really doing in these different parts of the transformer architecture.
Yeah, like what their specific roles are.
Right. Imagine a translation model that can adjust its attention on the fly, like when it's dealing with a really long, complicated sentence, and then optimize the decoder for fast, memory-efficient generation.
Some really thought-provoking stuff.
Yeah, it's a really exciting area of research.
So to wrap things up, this deep dive into cost-optimal grouped query attention for long-context LLMs, it shows us that there's a really promising path towards building more efficient and affordable large language models. And that's especially important as we keep pushing the limits of how much context these models can handle. But really thinking differently about how the model size relates to the configuration of its attention heads, and by getting a more accurate understanding of how context length affects computational and memory costs, this research gives us some really valuable insights for the future of LLMs.
I completely agree. And it challenges some of the assumptions that people have been making in the field. It shows that even small changes to the architecture, like tweaking the attention mechanism, can make a big difference in how practical and accessible these technologies are.
And for anyone who wants to dig into the details, the link to the paper is in the show notes. But as these models keep getting more powerful and those context windows keep expanding, it raises a big question. Aside from just optimizing those attention head configurations, are there even more fundamental ways we can change the way attention works in these models to make sure they stay usable and accessible for everyone? Thanks for joining us for this deep dive.